Hello everyone, welcome to week 10 for problem solving session. This week is for dynamic programming and today we are going to solve some simple problems from dynamic programming. So the first problem is uh, just one counting problem for the problem that you have already seen in the module. Uh, there was a problem called frog jumps or jumping stones. So this problem is derived from there only. So I'll give you some minutes to just read through the problem. So in the problem that we have seen in the module, the frog could jump only either one step or two steps. That is, if it were at stone number I, then it could jump to I plus 1 or I plus 2. But here we are saying that it can jump at most k stones. So it can jump from I to I plus 1, I plus 2 till I plus k. But it cannot jump directly to the last stone n. And here we are asking how many ways are there to travel to stone number n. So any ideas how to do this?
First of all, one confirmation.
Yeah.
What are the constraints for this for n k? Because we are not provided that in the problem.
Yeah, but it's only a counting problem. You can assume n to be, let's say, 10 to power 8. Yeah, that's a good valid question. So let's assume that n is uh, order of 10 to power 7 or 10 to power 7 or 10 to power 8.
And for this, I thought of a n into k complexity algorithm.
Mm-hmm.
So what we can essentially do is we can keep a record of how many stones we have to. I mean, how many ways are there to reach a stone. For let's say for stone number one, there is only one way.
Mm-hmm.
For stone number two, there is also one way because you can only jump from one to two.
Mm-hmm.
Then for stone three, we have two ways. We can directly jump to three, or we can come to three to through one or from two. So for every stone, we can check back the stones that are, let's say, k stones apart, and we can sum up all of the ways, and those all will be the ways of reaching this stone.
Hmm.
Uh, Therefore, we can calculate for every stone from 1 to n, and we'll get the value of n.
Yeah. Right. So for that, I think, yeah, constraints are important. It's if n is 10 to power 5, then k is, let's say, 10 to power 3 will do. Yeah. Yeah. So you have seen similar problem in the module also, right? The counting problem.
Yes, ma'am. It was about the two steps, like for frog.
Yeah. So the frog problem was in that you wanted to calculate that what is the minimum number of what is the minimum cost of reaching nth stone. if it were allowed to take 2 steps at every position I. But the third, I think there was one more counting problem which you have already suggested the solution, similar one, the dice problem, where you were asked that if you roll a die and if you are asked that how many ways are there to achieve a sum S, which is the sum of the numbers on the dice. Okay, so let's solve. Yeah, so here what you've suggested is correct. I'm just going to repeat it. Okay, so here we are saying that how many ways are there for the frog to jump to reach position I. So if I is equal to 1, then number of ways we can say is 0 or 1. I think both are fine. If I is equal to 2, the number of ways is 1. If I is equal to 3, then how many ways are there? It can, since it is allowed, so it depends on k actually. Let's say k is equal to here 4. Okay, so it can jump from 1 to 3 directly, or it can go from 1 to 2 and then 3. So there are 2 ways. And then when I is equal to 4, then it can go directly to 4, or it can go to 3, or it can go to 2, and so these are the cases here. So when it goes directly to 4, that is one way. Another way is when it first goes to 3, so then from 3 it goes to 4. So how many ways are there of reaching 3? That is 2. So this value is coming here 2. So it goes 1 to 3 and then to 4. So 2 ways from there. And then if it went from 1 to 2 and then one jump to 4, then how many ways are there? So that will come from here, plus 1. So total 4 ways are there. This one was when it jumped directly from 1. So maybe, yeah, this could be the 1 only value. So this is directly coming from here. And then when I is equal to 5, we will now when I is equal to 5, since we have said that k can be 4 only, so it can jump from 2 to here, so it can jump from 1 to 5 directly, or it can go to 2 and then to 5, or 3 then to 5, or 4 and then to 5. So it will be sum of all of these values, 1 plus 1 plus 2 plus 4. And when I is equal to 6, then it cannot jump directly from 1. It has to be at 2. Then it can jump from 2 to 6, 3 to 6, 4 to 6, 5 to 6. So it will be the sum of answers that we have for I is equal to 2 to 5. That is 1 plus 2 plus 4 plus 8. Is this clear?
Yes.
Is it clear to others? So here we want to calculate the total number of ways it can reach the nth stone, and we are saying that it can reach n. So it can reach n. Basically there is one condition: if it is at stone number I, then it can jump to I plus 1 to I plus k. It can jump to I plus 1 or I plus 2 or I plus 3 and so on to I plus k. So how can you reach n? That is the question. You can reach n from n minus 1. You take a jump from n minus 1, or you take a jump from n minus 2, or you take a jump so on from n minus k. I mean, these are the different ways you can reach n. Right? You cannot jump directly to n from any stone which is at a position less than n minus k. If first it needs to reach at least n minus k, then it can directly jump to n, or it reaches to n minus k plus 1 and then jump to n, and so on. So that is why, in order to find how many ways are there to reach nth stone, we take the sum of the ways the frog can reach these reach the position n minus k, or n minus plus n minus k plus 1 plus n minus k plus 2, so on, plus n minus 1, which is answer of n is equal to answer of n minus 1 plus answer of n minus 2 dot answer of n minus k. So to compute every value, it needs to know previous k values. And like for example, in this case, we have already computed. So let us put this in the form of an array, which is our DP table here. So initially, when I is equal to 1, how it can reach at position 1? There is only one, basically no step, but as a base case we'll consider it, let's say, one step. And then to reach at 2, so it to reach at 2, I mean, it is at 1, so it just need to take one step, so it will be 1. To reach at then 3 position, it can either jump from 2 or from 1. We are considering k is equal to 4 here. Okay, so it can jump, it can first reach 2 and then take a jump, or it can be at 1 and take a jump. So we add these two values, the previous two values, so it will be 2. Now to reach us at position 4, it can take a jump from any of these positions because they are still less than k, so that will be 4 here, again 5. Now again it can take jump of size 4, so again the sum of all of these values, 8. Now the 6, when we come at 6, now it can jump to 6 from 2, but it cannot jump from 1. So it first needs to come to 2 or 3 or 4 or 5. So that is why we take the sum of only the last 4 every time, if 4 are available, and this will be the answer here, which is, I think, 16. Yeah, and which you can see it's sum of like 2 to power, it looks like 2 to power n. What is the sum of the last 4? 16 and plus this one? No, it will not be 2 to power. No, it is 32. So it looks like it is like these are all 2 to power n something. I think it is like 2 to power n minus 2. Now if we leave the base case, does it make sense? So then I think that's why the constraints were not given for the problem.
Have we taken
Like,
for the last 4 elements?
Oh yeah, sorry, yeah, right. It is for
That
k
should be
is equal
15, I
to,
guess.
yeah, right. Yeah, it is for k, specifically for k equal to 4, but yeah, you're right. It's for k equal to 4, but if it is something else, then it won't be. Right. Yeah, thanks for correcting. So is it clear, this first problem?
yes.
Okay, let's look at the, so before we go to the second problem, which is knapsack for all subsets, I want to discuss the 0-1 knapsack problem. So I will describe the problem to you, and I'm sure most of you would be familiar with the problem already, and then you can just quickly, we can discuss it. So the 0-1 knapsack problem is that you are given some elements, say n elements. Each of the element has a value v associated with it, and so we have n elements v1, v2, v3 dot vn, and each of the element has a cost or weight associated with it, w1, w2, w3 and wn. And you are given the capacity of a knapsack, capital W, and you can pick any number of items, but you can only either pick an item or not pick an item. That's why it's called like 0-1 knapsack, means you can either pick a element or not pick it. You cannot pick some share of that element. Okay, and then you can pick any number of elements, but the condition is that the sum of the weights of the elements that you pick should not exceed capital W, and you want to maximize the value of the items that you pick. So for example, if we take here values as 10, 20, 30 and weights as also, let's say 10, 20, 30, and capital W is say 50, then what will be the value of what will be the maximum value? So in this case, since knapsack value is capital W, which the is 50, so you cannot pick all of the items because the total weight of all of the items is 60, but you can pick item. Let's say you pick item, if you pick only one of these items, so you pick one item 1, then you get 10 value, and the condition is satisfied, 10 is less than, the weight is less than 50. You pick item 20 only, sorry 2 only, value is 20. Picked item 3 only, value is 30. Picked item 1 and 2, 2 and 3, 1 and 3, 1, 2, 3, you can't pick crosses here. So if you pick item 1, 2, then the value will be 30, 2, 3 will be 50, and 1, 3 will be 40. So here the best is that you pick item number 2 and 3, and your knapsack weight is 50 and value is 50 maximum. So then the question is that how will you find this optimal subset with the maximum value, but the weight is less than capital W or equal to capital W. It can be both. So can you just quickly tell me in the chat that have you already seen that 01 knapsack problem or not? If all of you have seen it, then I will just quickly tell. Just it's like a refresher for 01 knapsack. Okay. Others, can you just quickly tell if you have seen it or not?
Trying to understand the problem first.
You have seen the standard 01 knapsack?
Not right now, but I'm trying to find.
Okay. And Balraj, have you also seen it? Okay. Sure. Then we will discuss 01 knapsack today, and the next problem we'll discuss next time. Yeah, if you're seeing this problem for the first time, it will take some time for you to, I think, understand. And so meanwhile, I can just look for some better example. You can think about it.
Just one clarification for this question.
Yeah.
In this knapsack of all subsets, so is it like we are taking all the subsets of this n numbers and like summing them up, and then the value that we get, I mean we are just like finding the sum of those subsets whose sum is s, like something like that.
So yeah, you are right in the sense we are going to look at every subset. So here also, when I try to solve the problem, I've looked at every subset which is possible, and I'm considering only those subsets whose weight is not exceeding capital W, and then choosing the best. The best is with the maximum value, which was 2,3.
Yes. So what I think here we are trying to do something like storing the weight, or I mean the sum of the sets that we have already encountered, and then building upon that, something like that.
Yeah, I mean that will be of course, I mean if you want to optimize it, then that will be required. You need to use some value that you have already computed, right?
Yeah.
In DB. But yes, the brute force is clear, right? The brute force is that if there are n elements, so there are 2 to power n minus 1 possible subsets, and then brute force approaches that you compute the weight of every subset. If the weight is less than capital W, then you take the value of that. I mean value is again the sum of all the values in that subset, and keep some temporary answer value, and store this answer as the sum of these values as the answer, and whenever you find something better, update it, and in the end you output that. Now the time complexity will be order of 2 to power n here, because we are going to look at each and every subset. Now can we do better, and how can we do better? If you will maybe you can then try to think on these lines. If it is not clear what I just said, then please ask me again. Is the brute force method clear? Kunal, Balraj, and
Yes.
yeah, okay. So, um, what can you say about each element? When you're thinking in terms of, say, a optimal solution, what can you say about an element? So we have two choices for every element. Either it be in the optimal answer or it is not in the optimal answer. Now that's an hint. So if you think in that direction, that for every element you have two options, whether to pick that element or not pick that element. Now what will happen when you pick it? The value will increase by its value, but the weight will decrease by the weight that of this element. And what happens when you don't pick this element?
So each element must be of maximum value and minimum weight, so that the most optimal solution would be at every point the value must be maximum out of all the elements, and the weight must be lower than most of the elements, or a combination of something like that.
Now you are suggesting a greedy approach.
uh, yeah, I guess at every point we have to take a greedy approach and fill the matrix with it, and then we can, I guess, find the solution.
Uh, while I know that the greedy does not work, so let me try to think of a case where it does not work for your such like what your approach. So you're saying at every time we are going to pick the element with the maximum value and minimum weight. So it is like if we have this sort the elements by value divided by weight, right?
Yeah, ma'am, something like that.
Yeah, sort the elements by value divided by weight and then try to do it. Hmm. So let's try to take this example that if we have elements 30 and 10, 45 with these are the values and the weights are, let's say, 10, 20 and 40, and capital W is equal to 40. So then what you suggested, will it work and how will it work? Is this valid? So here we have sorted them, let's say, by the ratio V by W. So V for first item it is 3, for second it's half, for the last is close to around 1.1. Then if we pick the one with the maximum ratio of value to weight, then we'll first pick the item number 1. Now the W value will be changed to 30 because we have already picked an item with weight 10. So next we want to pick the item with 1.1 V by W, but we can't because its weight is 40. So then we pick second item with value 10, weight 20, and the final value that we achieve would be 40. While we could have also picked the last item and achieved 45. So is this correct?
No, ma'am, this is not valid.
Okay. So any ideas on if we on those lines, let's say for every item we have two choices. Let's say for Vn, the nth item here, we have two choices, either to pick this or not pick this. So what will happen if you pick this? I mean, tell me what will happen if you pick this. Let me just erase all of this and I'm just going to write and you will tell me. So let's assume that we are going to pick nth item. So our answer will be what? Vn. We have picked the value. We have picked an item with value Vn. So our answer is going to contains Vn plus, now we have n minus 1 elements, right? So let's call this comma W. So can you help me fill these two blanks here? So I have picked the nth element. So my answer, which is the value, total sum of the values, is going to have Vn plus, now I need to recurse and look for in the rest of the elements what best I can achieve. So now how many elements are left?
Ma'am, n minus 1. If we are on the nth element, we are looking for the remaining earlier elements.
Yeah, so n minus 1 elements are left. And what is this knapsack weight, which is capacity, which is left with us?
The weight will be either the weight of the element that if we are choosing it, then we'll also increase the value, or otherwise we won't change the weight because we are not the max of both of these.
Yeah, right. So here I'm saying I'm picking the element. So what will be the weight of the knapsack?
W of n, I guess.
Sorry, can you say again?
It must be W of n. W of n value would be inside the knapsack, and the remaining constraint would be, the remaining weight would be W minus Wn.
Right. So the remaining is capital W minus Wn. So what is this? What is this saying? I mean, this term. What is it saying? It's saying that if I had only n minus 1 elements and my knapsack were of size capital W minus small wn, then what value could I have achieved? What value could I have got the best optimal answer? That I need to find out. Okay. Now this is one case when you picked the element. Another case is when you say, okay, let me not pick this element because I don't know whether it should be in the optimal solution or not. So that is the other case where you do not pick this element. So what will be these two values when you don't pick this element?
It will be n and capital W.
No, but you have discarded n. You're saying I'm never going to pick n. This was my chance.
Okay, so that will be n minus 1.
Yeah, right now you are at nth element. Yeah, you are at nth element and you are either going to pick it or leave it. So when you picked it, that was the first term. When you don't pick it, that's the second term. So you are left with n minus 1 elements.
And weight will be the same.
Weight remains the same,
W.
capital W. Now we have these two choices. Let's say somehow you had these are two recursive calls. These two are recursive calls. Let's say you ran it recursively. You got both of these answers. Now, how will you choose the best of the two?
That will obviously be.
I'll take the maximum of the two.
Right. Yeah, absolutely. So you just need to take the maximum. I don't know if you use curly braces or you just need to take the max of these two values. That will be your answer. So at every element you are going to have two choices, whether to take it or not take it. And if you take it, then the answer includes the value of the element, plus you recurse for the left remaining elements with remaining capacity of the knapsack. If you don't include it, then you recurse for the remaining elements with the original capacity of the knapsack. And finally you take the maximum of the two. Now, are you able to visualize it, like how it will be working recursively?
Yes, ma'am.
Okay. Does it also make sense intuitively? So here also we are actually going to so here so far we have not reduced the problem. Like how many, what is the time complexity of this?
This will be n square, sorry, 2 raised to n,
Yeah,
because we have two choices for every element.
yeah, right, absolutely. So we still have two choices for every element and the time complexity is still 2 to power n. Then how do we reduce the time complexity?
We can keep a record of the number of elements and ideally the value of n and w. And if we see a recursive call, if we have the value stored already, we can use that.
Yeah,
Just like
absolutely. Yeah,
memorization.
yeah. So here we, if you will take a problem, I mean, if you take an example with, let's say, 5 items, and if you try to make the recursive tree, you will see that there'll be a lot of sub problems which will be recomputed. There'll be many redundant sub problems, and if we uh, if we compute every sub problem only once and reuse them whenever we are having a recursive call, which is memoization, then we will be able to reduce the time complexity. Now in that case, what will be the time complexity?
That would be n into w.
Right, how is it n into w?
Because at most we'll have to calculate n into w calls. The rest would already be like stored in our memo,
Mm-hmm.
and we can call the value from there in O of 1, so that won't matter much.
Yeah, yeah, right. So the number of function calls, distinct function calls, will be capital N into, I mean, sorry, N into W, where W is capital W, the capacity of the knapsack. And this is because, as we can see here, every time we are going to visit every element, so N function calls are going to be there. I mean, N, this value will be definitely N, and then for every N we can have different choices of the knapsack capacity. So which are W choices? It can be for either 1, 2, 3 or up to capital W choices. So it will be number of function, distinct function calls is going to be n into capital W, and every function call is computing only if we memorize it. Then it's going to do a constant amount of time, which is calling these recursive functions and just taking the sum and then backs of that, which is a constant amount of work. So that's why the time complexity will be then order of NW. Now this was the top-down approach, and we can also do it in the bottom-up approach. So is the top-down approach clear? How we got this recursive relation and how we memorize it?
Yes, ma'am.
Okay, good. So the bottom-up approach also, let's quickly look at it because we have time still. So as you have already told me what will be the total, so the number of distinct function calls. So the similar question is that we have to answer in bottom up, that what will be the size of this table, TP table. So in bottom-up approach, we try to build the solution from smaller base cases. We first find the base cases, then we find the solution to the next bigger problem from the base cases, and then use the solutions available to the smaller subproblems to find the solution to the next bigger subproblem, and so on until we find the solution to the entire problem. So that's how we do bottom up. And generally in bottom up, we see that we have this table, TP table, and we fill the entries in this table, and we have to just follow some pattern how we fill it. It can be row wise, sometimes it can be column wise, and so on. But first we need to find what should be the size of this table, what will be the rows, what will be the columns here. So the size of this table will be n into w, and the rows are going to represent the items 0, 1 to n, and the rows are the items, right? I think I said correctly. And the columns are the capacity of the knapsack till capital W. And so on. Where each cell is representing that distinct function call or that intermediate value that we were computing in the recursive case. As ma'am has already told in the lecture videos, that in bottom up we might compute some of the values which may not even be required for the final answer, because we will compute all of the cells here. While in top down, we only compute those recursive values or those values, subproblems. We compute only those subproblems which are actually required to reach at the solution. So, like for example, it is possible that you will never achieve this, for instance, in the example that we had seen here with 10, 20, 30 knapsack, 10, 20 and 30 were the item values. 10, 20, 30 were the weights of these items, and knapsack capacity was capital W was 50. So this would be 50 from 0, 1, 2, 3 up to 50. These will be 3 items here, 0, 1, 2 and 3 items. Okay, now given that those values and weights, it's never possible that you will achieve an intermediate capacity, remaining capacity of the knapsack as 1, 2, 3, 4, 5, 6 and so on. Like many values are not possible, but in bottom up we are going to compute all of those values. So now let's move on. I think that will make sense once we discuss this. So what will be the base case here? So when we are at 0th row, which indicates 0 items, 0 capacity, so what will be the value that you can achieve? So every cell is actually a value. So if you have no item, so all of these should be zeros. You have basically no item. Now, when you have no weight in your knapsack, like this one, then what will be the, what do you think should be the value of this column, first column? So 0th row indicates you have no item. When you have no item, then the best you can achieve is 0 value. So we filled all of these, all of the items in all of the cells in the first row as value 0. When you have 0 weight in your knapsack, I mean the capacity of your knapsack is 0, then you cannot pick any item. So the best value you can achieve is also 0. So these will be the base case values that you are going to fill in your table. And after that, I think I should take some smaller values. Values, I think I can take anything. But weights I should take smaller, let's say 1, 2, 3, and capital W is say 5. And I'll just rub everything else. Sorry, it's removed everything else. So this is then our okay, and our answer will be this entry, the last one, which is dp of n w, which is indicating if we have n elements, capital W knapsack capacity, then what is the best value you can achieve. So that means any cell ij, what does that indicate? It indicates if you have I elements, I items or elements, and the knapsack capacity is j, then what is the value that you can achieve. And we have filled all the base cases. So let's go to 1, 1. So 1, 1 is saying that there are two options, right? Similar to what previously. So there are two options for the first element. Either we pick it or don't pick it. So if we pick this, then what will happen? We can pick this only if its weight is less than the remaining capacity of the knapsack. Its weight is here 1 and the capacity is also 1, so we can pick this, and value is 10. Okay, so max of 10 comma, otherwise we don't pick this. So if we do not pick this, that means we will look for the best answer in the previous row with the same with that capacity. Basically we are just going to look up. Okay, and so it will be 10 comma 0. We are saying maximum of 10 comma 0, so it will be 10 here. If we don't pick it, then the knapsack capacity remains the same as it is, that is j, and we can pick I minus 1 elements. So we will just look at the cell just above this. Compared to when we pick this, then we have the value of this, which is Vi, plus now the capacity of the knapsack is reduced from j to j minus Wi. Here j was what? 1, Wi was 1, so 1 minus 1 was 0, So we then look at dp of I minus 1 j minus 1, which was 0 diagonally here. So it is either 10 plus 0 comma 0. So the answer is 10 for this cell. So let me just write that here. What's that value for every cell? So dp I j is equal to max of dp I minus 1 j comma dp of I minus 1 j minus wi plus vi. We take the max and then fill this, and we will do this for every value, and finally whatever we achieve here will be the answer. So this is similar to what we did before. Here also we are saying, let us consider that this ith element is the last element. Actually the last element is n, but let's say ith element is the last element and the capacity of the knapsack is j. Then we have two choices. Either we pick this. If we pick this, then we will have the value vi, and we have already computed in the table. If I minus 1 elements were there, then I minus 1 elements j minus wi. What is the answer? Get that answer, add it, and that gives me this answer, this value. Or don't pick this. If we don't pick this, then I minus 1 elements are there, knapsack capacity is still j. This is the answer. Take the max and fill this. So is the bottom up approach clear?
Yes, sir.
Okay, yeah, thanks. Is it clear to everyone? Okay. So
Yes, ma'am, it is clear.
okay, thanks. I hope that the knapsack problem, 01 knapsack problem, and the solution that we've discussed is clear. So you go back and then look at 01 knapsack problem again and the solutions which are available on the web. Yeah, it's one of the classic problems in DP. Yeah, next, so this is it for today. So yeah, this is it for today. So let us discuss more problems in the more DP problems in the next week. If you so we have this problem was there in today's problem set. So do take a look and try to solve this, and we will be discussing this problem in the next time when we meet. So you can think of this problem as an extension of 01 knapsack problem and try to solve this. Okay, so that's it for today. If you have any questions, then please let me know.